The last thing that we have to deal with is the velocity of the water in the process of looking at the total energy in the system. How fast the water flows has a little effect on the amount of energy the pump also has to put to it to keep the pressure up at the end of the system. So the real key is to make sure you have enough pressure by the time you get out to where the sprinklers are to do exactly what you designed them to do. And then we have to pick a pump that can produce enough pressure to drive the amount of flow that we desire out there to get the job done. So we have a few things to overcome. We have to overcome the pressure of the nozzle, the exit, what we call the exit pressure. We have to overcome the friction in the main line and the laterals and all of the fittings, valves and so on that are included in there. We have to overcome the elevation differential. That could be a plus or it could be a minus. If it's going downhill, we get a gain power back. It's work the pump will not have to do. We can subtract it from its energy. If it's going uphill, we have to add more energy. Then we have a velocity head that we have to put into, and the velocity head is the energy it takes for the pump to start moving the water from a standing position, give it inertia to get it going down the line. Those all add together to create this thing called total dynamic head. In your textbook, there's a nice little discussion of that. If you add exit pressure plus friction head plus elevation head plus velocity head, it all equals up to total dynamic head. The total head that the pump has to produce to get the water to you, to the sprinkler. Now, a couple of things we have to be aware of in operations of that hydraulic system are water hammer, surge relief, and air relief. And we talked about these already when we looked at components. But we have the problem of water hammer where we try to, if we start a system up and try to fill the line too fast, we just send the water down that line just a racing. An empty pipe, valve comes wide open, what happens? The pump goes to very low pressure and very high flow. So now what we have is extremely high velocity of water filling an empty void as fast as it can run down that pipe. Well, that water might get up 20, 30 feet per second. Now water weighs 62.4 pounds per cubic foot. A cubic foot's not very big. And you have that thing going 30 feet per second and it hits the end of the pipe and you got a whole wall of that water, a whole bunch of those cubic feet coming on. Multiply that velocity times that cross-sectional area and times the weight of that water, and you got yourself a huge impact when it hits the end of that pipe. Hundreds of pounds of pressure being released instantly. Where can it go? Can't go anywhere. If all the main lines closed up, if there's laterals opened up, at least it can shoot down a lateral line. And as it goes down the lateral, it can start venting out the heads. So, you know, in best case scenario, when we open something up wide open and let her wheel, we got something open down there at the end that is going to start relieving some of that pressure. But if it's a closed line and there's no place for that pressure to go except to the end of the line, what it does, it hits the end of the line, and the only way for it to go is it's trying to seek a place to exit, so it goes right back down the pipe. And the weakest point in the pipe is going to blow. Or it's going to go back up and it's going to bounce back and forth until it stabilizes itself at a stable pressure. So that can be a real disaster in operations. Opening the line too fast. You want to open that thing so it fills slow. Now most people think like they're really causing a disaster when they just open that valve a little bit and it's a loud hissing sound and you think the world's coming to an end. But what you're doing is you're taking the energy out of the water and making it flow out slowly. So that hissing sound is your friend at that point, not your enemy. And then when the line fills, all of a sudden that hissing sound subsides. It means now the pipe's full. And then you can open the valve all the way open, and there's no velocity, no flow, so there's no velocity, and the pressure is all stabilized. Real nice and simple. Now, most all electric valves are designed to open slow enough so that they don't just send a wall of water down the pipe. They're going to open slow enough so that you don't get a water hammer. And in fact, these bigger systems, we get into agriculture and are flowing many thousands of gallons a minute, those valves are staged, and you actually set the times of their opening, and you can put them into multiple stage opening and how far open they'll open per stage, so that you very gradually will fill some of these very big lines. Because it can take a tremendous amount of water to fill up like a 6-foot main line. We're talking main lines, you know, diameter that big. And we might have 20 or 30,000 horsepower on the front end of it putting water into it. Not uncommon. So we're talking some serious energy potential on some of these systems.